Okay, so welcome back. So we are coming to the last part. I hope we won't take too much time to finish the last part. So since this IU programs relate to the AI, I think not only the robotics in AI and also I think 5G other aspect, the biology, other areas in AI. So I just talk a little bit about how robots and AI they sort of connected. Okay, this will be a little more high level, kind of talk about the general connection between the robotics and AI, and there will be individual workshops talking about the specific techniques in the AI, like the Dr. mentioned earlier. So let me see if I could do this. Okay, I'll see my full screen. Okay. So how can AI help robots? So there are a couple, like I mentioned, the three components earlier. One is modeling, one is sensor, one is control. They actually each component can be helped by AI. For example, in terms of modeling components, we can have a fairly abstract representation of robotic dynamics. For example, using the ODEs, the PDEs, the other different methods. Another approach that has been done by people recently is on the robotic dynamic program modeling using the kind of recurrent neural networks. The reason this does not include the convolutional neural network is because convolution is more like for static one. It's more like the time series data. So you can use LSTM gated current unit and even other methods, which can model the time series data. It can provide a more accurate model. But of course, the training data can be an issue, especially for the online training. The second aspect in terms of modeling is environment modeling. So how do we understand the environment? For example, how do I understand the target, to recognize the target and the sign? For example, you use a convolutional neural net to recognize if it's a stop, is a speed limit or whatever. And also can be the localization mapping. For example, computer vision can be used in the modeling components. For the sensors, AI can actually help in terms of data denoising, cleaning, machine learning. That even the traditional machine learning methods can be very helpful. Data fusion methods like a Bayesian distributed multi-agent, they kind of fusing can be very helpful to actually provide more accurate data. The sensory processing of sensory data. Okay, in terms of control, there are a couple techniques. The fundamental one is called reinforcement learning methods. It's very, very important and become very popular these days. And there are also other methods, including imitation learning, inverse reinforcement learning, and multi-agent reinforcement learning. So they actually try to help improve, kind of provide more like advanced control techniques. I'll talk about a little bit about why those learning methods are kind of important when we compare with traditional methods. Okay. So convolutional neural networks. So this is a class of deep neural networks that most commonly applied to analyze visual imagery with application in a number of areas. I don't think I need to talk too much about this one because this is really popular. The kind of the starting point of the deep neural networks. So it shows the tremendous success and improvements over the traditional methods by recognizing these different type of objects and provide a very high accuracy. That's what the convolutional neural network can do. Okay, so many different applications so far. So the second one is called recurrent neural network. So one type of the network is they're kind of different type of the difference between the CN and NN is I understand it's also a class of deep neural network, but it's trying to understand the temporal dynamic behavior. So the previous one is trying to understand more like static visual imagery, and this is for temporal dynamic behavior, which means you have time associated with that. So this was also a kind of application in robotic control, time series predictions, and anomaly detection music compositions. Okay, so LSTM is one of method. There are also other type of method structure that people propose for the okay, and data cleaning. The goal is to clean and correct, even remove the corrupt and inaccurate records from a record set, a table, a database. Okay, this is pretty important in different areas like finance, airplane, transportation, social network, all the stuff. Okay, biometrical data. So data fusion is trying to integrate multiple data sources to predict more consistent and accurate and useful information that can provide by any individual data source. So the older days, we don't have a lot of data, so data fusion can be like using Bayesian-based approach, but these days it can be very, very challenging to using the traditional Bayesian-based approach. So new data data information-based AI techniques have been proposed to actually address a number of challenges. Okay, especially for big data, it's kind of challenging. Okay. So last part, I'll talk a little bit about control. As I promised and mentioned before, I talk a little bit about this control reinforced learning aspect, and to tell you why reinforced learning is kind of important. The traditional controls, this is what is set up so of the reinforced learning environment, the framework. What it does is trying to say, if I'm as agent, you can consider this a robot. If I'm going to take action and it actually apply to certain environments, and we will have a transition to another state, move to another state, and then we have some kind of reward associated with that action, and that transition to the next state, basically. Okay, so this is a pretty broad definition than the modeling I mentioned before. If you still remember, I talked about modeling. You have an input and output. This is more generalized than that. And also in the traditional modeling aspect, we have to have sort of like ordinary differential equation or things like that for us to design a control algorithm. But reinforced learning relies, this is very general. This is also kind of pretty similar to our interpretation about the world. So when we have a robot which interacts with the environment, we have some kind of reward, and then we take action that will transit to another state. That's kind of very natural to our thinking process. Okay. So this is a general structure for reinforced learning, how we actually do, okay, what is the goal and what is trying to do, okay? So reinforced learning is an agent, like I said, interaction with a called Markov decision process. So the Markov decision process, long story short, the Markov decision process means your current state. Let's say you are starting at a certain position, you take action. All the future states will only depend on your current state and your current action. It will not depend on your past action, okay? Or past state. Of course, your current state action your current state will still depend on your past, but which means only your immediate past will kind of have impact, not the history. Okay, that's what the reinforcement learning is trying to, what MDP means. Okay, this is pretty general, but it may not apply to all the scenarios, because in some scenarios, your history does play an important role in your future state, which may not be modeled by the Markov decision process. Okay, so the task of reinforcement is actually to find a control policy to yield the maximum cumulative reward. What is the maximum cumulative reward is because at each action, you take action. In the previous one, you do have a reward over here, right? So you collect a reward. This T plus 1 means at the current state, you take action, you get a reward. And this is what you have next step. You take action, you have a reward, and so on and so forth. Of course, this gamma is called discount factor, which means your future reward may not be as important as current, right? For example, you get some money today, you can spend it. But if I promise you the same money in 2 days or in 2 months, it may not worth as the same as right now, especially considering inflation. Okay, so you sort of consider this discounted cumulative, which means you're trying to compute the sum of everything, and you're trying to maximize those. Okay, then this is the policy. The policy you can interpret it as at one state you want to take action. The policy is a map between the state and the action. Of course, the policy can be deterministic, which means at a certain state you only have one action to take. For example, if you're talking about navigation from A to B, at a certain state, you only take the action. You all take the action. The other one is called stochastic. You can take at the state, you can take action with certain probability, or take another action with another probability. Of course, the probability should sum out to be 1. It cannot be like a probability of more than 1, right? That can all be represented by the policy, okay? Right? So I mentioned before, the MDP process is, so if I give them all the MD process, you start from somewhere, and your goal is, let's say over here, you can move backwards, you can move up and down. Of course, when you start over here, you cannot move down, you cannot move to the left. And another location, you can move up and down, left and right. And if you take action, you can get, let's say this state, you cannot reach there, okay? And at a certain state, you can take action and you can collect a reward. The reward can be positive, it can be negative. If you reach a goal, you get a positive. If you reach some area, there's a cost, which means you get a negative reward for that, okay? And the goal is, let's say my goal is I want to find a policy which can drive me from beginning to the end, which can give me the maximum cumulative reward. That's sort of what the reinforcement is trying to do. So if the environment is already given. I know the environment really well. So you actually can find the optimal control policy by using dynamic programming. If the transition probability, if I take action, the probability transition to the next step, I already know it. And if I start over here and move to the left, right, I know how the probability transition to the next one. If I know that, you can actually find the optimal control policy. You don't need to use reinforcement learning because the dynamic programming will do it. Okay. Now, what the reinforcement method is it doesn't require that you know the transition probability, which means I don't know. I know your transition, but I don't know because reinforcement is sort of will learn that probability because try to maximize the cumulative reward in that way. Okay. So the typical reinforcement method include a brute force. Okay, you can evaluate all the possible policies and select the optimal one. That's when you can do that. That's pretty straightforward, but it's, as you can imagine, it's time consuming because you have to evaluate all possible policies, right? The next group of reinforcement methods is kind of value-based methods. You actually select policy that maximize the expected state value or state action value. That's kind of directly based on what it's trying to do. Okay. The next type of typical method is called a policy-based method. You normally start with a random policy and you're trying to figure out the direction you should go to improve your policy, right? This is you don't have any policy to begin with, but you actually try to figure out the value or state value or state action value. You try to maximize that. You find a policy that can maximize that, right? Eventually, you start with a policy. Normally it's parameterized by some parameter. Then you try to find a gradient which can actually improve your policy. Okay, that's kind of the approach. The deep learning methods can be used in the reinforcement learning. People call deep reinforcement learning, trying to use the deep neural networks or models that actually can help us to learn a lot the state the control policy, especially for high dimensional state or state action spaces. So that's kind of what difference. It can be used to approximate the value function. For example, you can use the deep neural network to actually approximate value. And typically for the policy, you don't have a deep. You can have a little bit deep, like 2 layers, 3 layers, but not too much typically. Right? Okay, so like I mentioned, reinforcement learning does not require you know the transition probability, which is one fundamental difference between this kind of reinforcement learning based control and the traditional control. Because if you don't know the probability transition probability, you cannot design control algorithm. You don't know what it means, right? Okay. So the advantage of reinforcement learning based algorithm is no requirement of prior knowledge on models. So you don't need to know the transition probability as long as it is MDP, okay? And as a matter of fact, MDP and Markov decision process is pretty general because it only requires the future state depends on current state action, but no past state action. So one thing I want to emphasize, it does require the transition probability to be constant, to be the same. If the transition probability changes over time, that's a different story. That's called changing environment, which may not be solved find a good solution by using reinforcement based, right? Because reinforcement require you have a constant one, right? And it's easy to interpret. The goal is to maximize reward, which we can define. If we design good reward, which will give us good performance, and actually it's match what we want to see. And it's good at dealing with high dimensional systems such as working robots. But the caveat is when we try to work with high dimensional system, reinforcement can require a lot of data sets and require a very long training time, and it may not be stable all the time. Okay. Also, reinforcement learning can work well with long-term planning, such as a Go game, because you have many steps, because you all play with your opponent for many steps. So Go games can the reinforcement learning can provide a good solution that way, but it does not. It also requires long training time and also samples. Like you have many examples that can provide to the learning agent. So disadvantage of reinforcement learning. So first of all, it's slow training. Typically require a lot of time to do the train the algorithm. The reward assignment for missions can be challenging because you make a slight change to the rewards. It may change the policy dramatically. So they also are challenging in terms of collecting more reward or finishing tasks. For example, if our goal is only to collect reward, why don't we continue working in the environment without finishing the task? So how do we solve the challenge of collecting more reward versus finishing task? You can assign a high reward to when it reaches the goal, for example, but it doesn't mean it will go to the goal because it will continue collecting the reward if you don't assign the reward correctly. Also, reinforcement suffers from the local optimality because let's say you use the policy gradient, you're actually using the gradient. The gradient only go to the local minimum, but not go to the global minimum. So the exploration become an issue. in terms of finding the global optimal position solution. And normally it's very hard to understand the control policy. If you have reinforced learning algorithm, you have the map. Actually, it's not easy to understand what that means. Okay, but for the physical, the practical control, we develop the traditional ways. We know they say we have a feedback, we have grading of certain component, then it's fairly easy to understand. Okay, and lastly, the reinforced learning only provides statistical optimization, but not a guarantee of the performance on each run, which means statistically reinforcement can provide a better performance than the other method. However, it doesn't mean at each run you will get the maximum, your best performance. Okay. So imitation learning. So I want to speak a little about imitation learning. Imitation learning trying to use a supervised learning to learn the control policy by mimicking experts to demonstrate feedback. So this imitation is more like kind of supervised learning, or like the convolutional neural, kind of that. You sort of give an expert demonstration and you actually supervise your policy, normally represented by parameters, for example, and you try to figure out the best parameter associated with the neural network, for example, which can provide the policy that can mimic the demonstrations. Okay, so it's more like supervised. You don't do like, it doesn't involve a lot of kind of reward like I mentioned over here. Okay, it's more like you want to train your policy, try to match what you can get from the experts. Okay, the inverse reinforced learning is a good technique because I mentioned the reward can be challenging to assign by users. So why don't we just learn reward, right? By giving expert demonstration. Let's say expert likes that, we can actually try to find the derived reward from the demonstrations. That's called the inverse reinforced learning. So what we're trying to do is try to infer reward from the environment based on the demonstration. The one caveat for that is the learning reward is not unique, which means you may get a setup because if you scale up and down internal reward, it does not change the control policy. Okay, there are kind of two different types. One is called, if the model is given and it becomes simpler because we already know the model, we actually can run full reinforced learning, and assuming we have linear reward function, we can have a policy and compare that policy, compare the policy, the general trajectory using the policy with that given by expert. We can update the reward and then continue to run the full reinforced learning. And if you model free, which we don't know, model is not given, for example, then we have a little bit more complicated process to actually understand learn the reward function. Okay, I wouldn't talk too much about the differences. If you're interested, you can actually check online to see the difference between these different methods. Okay. So last one is called multi-agent reinforced learning. So which means we have multiple agents. They are actually working in the environment. They could cooperative, they could just not cooperative. Okay, and what they're doing is actually working in the environment, and the goal is actually to derive the policy or actions for different agents subject to certain goals. The goals can be cooperative, can be non-cooperative. Okay, the main challenge for multi-agent reinforced learning is the observations reward. They are kind of separated because each one can have its own observations reward and take its own action. Even sometimes the agent may not care about what agent is trying to do, so it makes it a little complicated. And also for each agent, as you can imagine, the other agent will also change the environment. That's why it's kind of dynamic environment. Even the actual environment is not changing, but the other agents are actually changing or taking action. So it makes for one individual agent, actually the environment is changing. So that's it's very challenging to design the policies, and even the framework can be very challenging. The other challenging is a lot of times each agent can only know the local information, which means they only know a few of them, not all know everything else. So the action, how do we get the action policy, which can be very challenging, especially when we have some global objectives. How do we, translate the global into the local objective and to create a local action policy? That's kind of challenging as well. And the last one is a multi-agent reinforcement also can deal with the game environment, competitive games, like one agent that play against each other. They may not necessarily play with each other. Okay, so that can be also challenging. Okay, so I don't know too much about this. The multi-agent becomes really popular these days in gaming environment, in different strategies, different strategies for multiple players. Okay, so now I'll give you a brief summary. It's pretty high level. I know it wouldn't take too much to talk about what we could do, but I think this just give you a summary about what we can say about the robots. So now, the first one, I think robots become more capable and intelligent these days. So we can see either toys, other things, even including robotics, autonomous car. It become really capable and intelligent, and sometimes really smart. For example, the AlphaGo, AlphaZero, they can be the human players in the Go game. It's kind of really amazing. Robot can indeed replace human in challenging, boring, and dangerous tasks. Okay, that can help us a lot. Robot and AI are closely related, especially if we want to develop more intelligent robots. So the intelligent robots actually depends a lot of the techniques developed in AI. Of course, built on a lot of these fundamental studies using in the traditional disciplines. And also, robot can be dangerous if you're not operating and they're not operating designed well. So, especially when we work with drones in our lab, for example, work with drones, they can crash, they can cause damage to the properties and even the humans. The other one is even for the autonomous car. If you see the news, there are also some of the issues in terms of safety issues. It called car crashes, and even we use the AI techniques, it may not actually give us all the good performance all the time. So that means they can be dangerous. So be careful when you work with the robot, especially with the physical robots. Lastly, I think robotics is a highly interdisciplinary area if you want to get it work. Okay, you can actually separate the task into small components, but if you really want to work in the real world environment, it's challenging. So you have to work with communication, the hardware, the software, the programming, the algorithm, all different aspects. So a lot of time when people ask, can you get this done? I think it's very challenging to get it done. But of course, on the other side, it can be a lot of fun if you really can get it done, see it work, because robot can work in the right way you want. I think it can be very fun as well. So I think with that, I'm going to stop. I don't have much to say now, but if you have questions, I'll be happy to take any question you might have, and maybe have some discussion.